arithmetic here, and then I'll get back to RSA. We got time to do them both tonight, and it's a good thing to do. So let me get rid of the cahoots. All right, let's go here. All right, so here's modular arithmetic. Shrink this down a bit. All right, you've seen clocks. Clocks use modular arithmetic. In modular arithmetic, instead of having numbers that just get bigger and bigger, you just go around a ring. So you start with 0, you add 1, you get to 1. You add another 1, you get to 2. And when you get to 8, when you add 1, you're back to 0. You go around the ring. They call it modulus 9 because there are a total of 9 symbols, including 0, and you never use 9. So 0 mod 9 is 0. And 9 mod 9 is 0. Take 8 plus 1, you're at 9, and that's the same thing as 0. And 17 mod 9 is 8. So you can figure it out by walking around the ring. You can also take the number and divide by the modulus and keep the remainder. So 12 is 1 times 9 plus 3. You keep the 3, that's the modulus. 17 is 1 times 9 plus 8, so the mod is 8. That's modular arithmetic, and this is real important in cryptography. This is how RSA works. It's how most cryptography works, because if I'm going to encrypt something like a byte that has 256 possible values, I want the encrypted version to still just be 1 byte. I don't want it to get bigger. So you work on a ring where you only have a certain number of values possible. All right, so here we are at bigger numbers like 27 mod 9 is 0, because that's 3 times 9 plus 0. 28 mod 9 is 1. That's 3 9s plus 1. And so it's 3 times around the loop, and 1 more, so you end up at 1. All right, you can have negative numbers too. So if I start at 0 and go backwards, minus 1, I get 8. So minus 1 mod 9 is 8. Minus 2 mod 9 is 7, and so on. You can go backwards. Negative numbers are fine, positive numbers are fine, but you always get an answer between 0 and 8. So you can add numbers. 0 plus 1 mod 9 is 1. 1 plus 5 mod 9 is 6. Now 8 plus 3 mod 9 is going to be 11 mod 9, and that's going to be 2. 9, 10, 11. So you can commute these. If I have 15 plus 13 mod 9, I could first add 15 plus 13 and get 28. And that's 27 plus 1, so mod is 1. I could also apply the modulus separately to each of these numbers, 15 mod 9 plus 13 mod 9, and that would give me 6 plus 4, which would be giving the same answer. So that's a way to get there. You can do subtraction, 7 minus 2 mod 9, and so on, and you can do the subtraction first and then the modulus, or you can do the modulus on each term separately and then subtract, and you'll get the same answer. So here's some examples. If I work at mod 4, it's even simpler. There's only 4 numbers. So 0, 1, 2, and 3, mod 4 remain the same, but 4 mod 4 is 0, and 5 mod 4 is 1, and so on. Here's modulus 6, 0, 1, 2, 3, 4, 5. And when you get up to 6, it's 0, and 7 is 1, and 8 is 2. 8 mod 6 is 2, because 6, 7, 8. All right. So let's try some modular arithmetic. Make this bigger. Bigger, I say, not brighter. There we are. All right. So what's 899 mod 9? You can put a number in the chat. Yep, it's 8, because 900 mod 9 would be a multiple 9, that would be 0, and it's 1 less than that. So you go backwards 1, you get to 8. Very good. How about 8 mod 4? That's 0, right? Because it's 8 is 2 times 4 plus 0, so it's 0. Good. How about 8 mod 7? That's 1 times 7 plus 1, it's 1. All right, you folks are getting it right. That's good. So let's try the next bit of modular arithmetic, which is a little more mind-bending, which is modular inverses. And this is what we need for RSA. So, all right, we talked about this, mod 9, you understand that. So you go up to 8, and then when you have 9 mod 9, you're back to 0. So if I take 2 times 9 mod 9, 9 mod 9 is 0, so I'll get 0, 2 times 0. If I take 2 times 10 mod 9, I'll get 2, because 10 mod 9 is 1. So I can double a number. Now, if I take 2 times 9 and 2 times 10, we've done that. Now, what if I take 2 times 5 mod 9? That's going to be 10 mod 9, which is 1. So this means if you find a number where you're multiplying it by this, multiplying 2 numbers together and you get 1, that means 1 is the multiplicative inverse of 2. That means if I encrypt by doubling a number, I can decrypt by multiplying that by 5, because the combination will be to have multiplied by 2 and 5, and that's the same as multiplying it by 1. And this is how RSA encryption works. That's why we have an encryption key and a decryption key. You encrypt by multiplying by this number, really exponentiating by that number, and then you decrypt it by taking that and just multiplying again by a bigger number to decrypt it, because the combination of 2 is effectively a 1. So here, we're going to take a key of 6 and try to encrypt stuff with a key of 6. We take 6 times 1, 2, 3, 4, 5, 6, 7, 8, 9. But the problem is 6 is a not relatively prime to 9. 6 is a multiple of 3, and 9 is a multiple of 3. And that's a no-no, as you're going to see, because 6 times 1 is 6. 6 times 2 is 12, which is 3. 6 times 3 is 18, which is 0. And you just get 630, 630. And we've seen this before. If you have a transformation where you take input data that has a wide variation and the output data has less variation, you have destroyed information. This is what was wrong with the AND and the OR operation for bits. Now, why we had to use XOR. This destroys information you're not going to be able to decrypt, because if the encrypted number is 0, I don't know if the original number I fed in was 3 or 6. It could have been either of those. There's 2 possible numbers. There's really 3, also 0, that could lead to the same result after multiplying. So multiplying by a number that is not relatively prime with the modulus destroys information, and you can't use it. But 7 should be okay. So if I take 7 times 1, I get 7. 7 times 2 is 14, which is 9 plus 5. 7 times 3 is 21, so that's 18 plus 3. And 7 times 4 is 28, which is 27 plus 1. So I've found the multiplicative inverse of 7 is 4. And there's no easy way to figure it out in your head. You just have to try numbers to find it. There is an algorithm to find it on a computer somewhat faster. So here's modulus 4. So if I start multiplying 4 by various things, 1 mod 4 is 1. 2, 3, oh, there's 12 mod 4, that's 4. All right, I don't think I need that one. Anyway, so that's a multiplicative inverse. Let's see if you can do some of them. Those are more difficult. All right, so what's 8 times 2 mod 9? Yep, 16 mod 9 is 7. It's 1, 9 plus 7. All right, what is the multiplicative inverse of 3 mod 5? Now, let me show you how I'm going to do this. I'll show you the method. You take 3 times 1 mod 5, and then 3 times 2 mod 5, and just keep trying more of these. 3 times 3, until you get an answer of 1. Just try all the possible values, and there aren't that many. And when you find one that gives you a 1, you found the multiplicative inverse. I say, I guess the mod 5, there's going to be 3 times 4. And in principle, you could worry about this one, although that's obviously not going to be 1. So which one of these gives you 1? 2. 3 times 2 mod 5 is 1, so there is a multiplicative inverse, and it's 2. All right, how about 8 times 2 mod 7? That's, I think I don't have a new answer there. That's 2. 8 times 2 is 16. That's 2 7s plus 2. All right, 5 times 2 mod 6. That's 4, right? This is 10 mod 6, which is 6 plus 4. All right. And how about this? The multiplicative inverse of 4 mod 15. So remember, you're going to do it this way. You're going to do mod 15. And you're going to take 4 here. And have more of these, like 4 times 5, mod 15, and so on, until you find something that gives you 1. Yep, I think you got it there. 4 times 4, mod 15 is 1. So 4 is its own inverse. So if you encrypt by multiplying by 4, you decrypt by multiplying by 4 again. All right. Good. All right. Anyway, that's all I wanted to show you of that stuff. I'm going to stop this recording.